Just to remind you, problem set 3 is due on Wednesday, so 2 days from today in class. And on Friday is the first midterm exam. Hopefully, though, I've encouraged you already to go and take old exams. In part, it's preparation for the exam. It's part of the learning process. One of the ways you learn is with pressure. You end up having to learn this material. Those of you who are trying to access the old exams from off grounds will have to go through a password access version of the site. And the password, it's on Colab. It should be, should be there. It should be working right. I turn off the sound for a second. Not to spread my questions all over the internet. Anyway, any questions about problem sets or exam stuff? All right. Where I left off approximately last time was talking about static electricity and the idea that, of course, you separate, there's this conserved quantity known as charge, and you can accumulate some positive amount of that and some negative amount of that, and the attractions and repulsions between them, opposites attract and so on. And where that took us then is into the idea that you can store energy in the attraction or repulsion between these accumulations of charge. And that energy is, we call it electrostatic potential energy. And associated with electrostatic potential energy is a physical quantity known as voltage. Voltage measures how much energy per charge there is, electrostatic potential energy per charge there is at a certain location. So a location that is full of positive charge, there's just tons of it around and not much else that's of interest nearby, that's likely to be a region of high positive voltage. Meaning that if you were to take a small amount of charge at that location and let it escape way off into the distance where it was free of energy, it would release a lot of electrostatic potential energy. The charge you're taking away is a positive amount of it. Releases energy as it escapes other positive charge. And so this region had a positive amount of energy per charge. Therefore, a positive voltage. So far, so good? This is the real meaning of voltage. The peculiarity is that regions where there are a lot of negative charge around and nothing much of interest nearby, those regions tend to have large negative voltages, meaning that they have a lot of energy per charge, but it's a negative per negative charge. So that division by a minus amount gives you a negative value. It's a negative voltage. And what's going to become important as we start looking at electric currents flowing from one place to another, like through a flashlight, which is one of the next topics coming up. The charge, and without the modifier, it's positive charge. Positive charge loves to go from high voltage to low voltage because that's the way it goes to release energy. It's typically leaving an accumulation of positive charge, which it hates, and going towards an accumulation of negative charge, which it loves. So it's it's pushed away and then pulled in. The whole process, if you're holding on to that charge, now I can actually hold one. Here it is, positive charge. As you hold it, you have to hold it back. It's trying to leave the positive charge over here in the high positive voltage area, and it's trying to it's attracted to the negative charge over there. Gets sucked on in. So the whole process, it does work on you. And that kind of work, okay, it doesn't do it on a person, but it does it on all the gadgets you have ever dealt with that are electrical. Your cell phone, your computer, all these gadgets, your television, all these electronic computers, basically. The bottom line, though, is that it's that energy being released, that electrostatic potential energy being released in the flow of charge, positive charge, from high voltage to low voltage that powers everything. So the lights, these cameras, the projectors, the computers I've got in front of me, the laser pointers, it's all that process. Okay? Well, that brings me, at least I've tinkered over the years with different topics. Xerographic copiers remains one of my favorites. for this sort of this territory. We're looking at how electric charge moves around and why, and voltage, and what are the issues here. And xerographic copiers are all these, the photocopiers that you're used to using. That process was invented, I think, in the 50s. It was the foundation for a company called Xerox, which is now, I guess, has been bought up by some other one. I forget who just recently got it, but basically it's followed its whole life trajectory, and now it's not a big company anymore. It was, for a while, the dominant photocopying company in the world. They invented it. So the way it works is electrostatic. It uses electric charge to move around a fine powder, typically black, but it can come in other colors as well, to place fine powder onto a sheet of paper, most often, and then press that powder into the paper or melt it into the paper to the point where you've got an image there that's permanent. So all these copies that I have in front of me that you've ever made most of your life, they're using this technique. And furthermore, all the printers now, you have sort of seen this transition from laser printers being one device and copiers being a different device. They've kind of blended together to the point where they're sort of only partly distinguishable. They use the same concept. The only difference between a laser printer and a xerographic copier really is in the xerographic copier, you typically arrive with a physical document that you're trying to duplicate, whereas the laser printer is only a virtual document. It's in some computer's memory, but it doesn't actually exist on paper. Otherwise, the printing process is the same. They're using light to create to position a pattern of powder, and that involves static electricity. So that's just a preview of the story that we'll go through. So, seemingly unrelated question, but here it is. If you're covered with static electricity, which say it's a winter day when there's not much moisture in the air to cause trouble for static electricity, so you're going to accumulate a lot of it, and you've walked across the carpet, you're just decorated with charges, I don't know which one they are, positive or negative, doesn't matter. If you hold a sharp pin in your hand, and you reach out to some big metal object, maybe it's the doorknob, maybe it's something that's large and metal, to which charge from you would love to go, are you going to get a worse shock than if you just reached out with your bare hand? It's going to be worse, the same, less severe shock. You okay with the question? I mean, basically, how's a pin going to affect the shock you get? A, it'll make the shock worse. How about B, it'll make the shock weaker. Okay? And how about it'll leave the shock unchanged? So that's pretty flat. There's almost no difference. You're spread out, those of you who are voting. The Vonnegraph we were playing with the other day had a problem where the belt, remember the rubber belt that's in there that's carrying charge from the bottom to the top and leaving it up there on the top? It came off its little wheel, its little pulley at the bottom, and it's not very well, it's unhappy. So this guy's the Big Bertha. Let me turn it on. There you go. It's got a pretty good smack to it. That's the charge leaving this surface. Again, it's probably negative charge. I haven't checked this guy. But it's going into that ball and from there into the ground. So this is a way that the charge can escape through the air to this ball and then leave. So the question is, if I go up there with my hand, I'm not getting, usually I get zapped at some distance from these guys, but not today. Why not? I'm getting little sparks. Okay? So here's the needle, and whether I have the charge and I'm going to something that has no charge, or whether I have no charge and I'm going to something with charge, the story is pretty much the same. The charge wants to spread out Whether it comes off me onto that or off that onto me, same story. Very little difference. So here's me with a pin. Nothing. That's the point. Nothing. The answer to this question is the shock gets weaker to the point where there's no shock at all. Why not? Let me get rid of this thing. It's still working. But the needle kills it. Stop. So at least I hope that's, I'd love to have the sparks this long and consistent. I'm not quite sure why not. Try this guy. Not clear. Okay, it doesn't want to shoot at me either. The observation here is in answering this question is that that sharp needle ruins the whole process. There's no big lightning bolts that occur at all. There's no shock at all. So, I mean, simple result of this is, okay, if you're covered with electric charge, having walked across the carpet, and you know that when you reach out to your friend or to the wall or something like that, there's going to be a big spark that's going to leap. The solution's easy. Just hold the pin in your hand as you make that move. No spark. The pin ruins it. And what the pin is doing, and this is where we're going to go, is the pin is letting charge leak out into the air, and it gets ferried by particles in the air, actually air molecules, dust particles, the works. They end up picking up the charge and shuttling it across. In this case, if that thing was negatively charged, which I believe it was, when I reach out like this, it's going to polarize me. I may be electrically neutral, but remember electric polarization? That I have positive and negative charges in me. So when I reach out to that negatively charged thing, it's going to attract positive charges to the extent they can do it closer and repel negative charges farther away. I'm going to end up with a net displaced charge. I'm going to have positive charge on my hand and negative charge everywhere else. So far, that's okay? So as I reach out with my positively charged hand near that negatively charged ball, the opposites attract. If I just do it like that, a lightning bolt goes zapping through the air. And that by itself is an interesting phenomenon, that it manages to get the air to conduct electricity, despite the fact that air is basically an insulator. The story of that lightning bolt I can come to. What are the issues? You can actually tear electrons right off of the atoms and molecules in the air. When you do that, when you break apart what was a perfectly happy and electrically neutral atom or molecule, you end up with a positively charged remnant of the molecule or atom and free electrons. And they can exist in the air. And to a very slight extent, they do exist in the air. Within my hands right now, there are hundreds or thousands of those fragments. They're there not for an obvious reason. They are there because of cosmic rays and natural radioactivity and stuff. There are things whizzing through us all the time, sent along by processes out in the cosmos. And the result is they break some of the atoms and molecules en route. They're what are called ionizing radiation, meaning that an ion is a piece of an atom or molecule that has a net charge. In this case, typically it's a net positive charge because an electron got knocked off it. So anyway, in my hands there are some hundreds or thousands. I used to know the number properly, but it's a modest number of fragments that have electric charge. And as I reach out here, those tiny fragments that have charge begin to move back and forth between us. The positively charged ones go whizzing towards that negatively charged thing. They love it. And the negatively charged ones in this area come whizzing toward me because I'm positively charged and they love it. And if they have the opportunity to hit things en route, which they do, they can knock charge out of atoms and molecules that they hit. They can shatter them. it's not a, yeah, we'll call it shattering them. And that can cause more particles to come apart, more atoms and molecules. It's a catastrophe. And that's what the spark is. The spark is a catastrophe where we get to the point where the charges begin to hit each other so hard as they're trying to shuttle back and forth between us that they begin to knock each other apart. And suddenly a channel opens up, which is filled with charged particles that can carry electricity nicely. And that's the brilliant blue flash that you see. It's a lightning bolt. It's all the same physics. Okay? So it happens in a catastrophic bolt. Prior to that happening, not much is going on, and suddenly, bam, the whole thing opens up. Just a channel of charges smashing into charges, the atoms, and making more charge that's free, and so on. When I go up there with that pin, the lightning bolt doesn't happen. Why not? Because the pin allows for a continuous exchange, a very gentle exchange of electric charges between me and the ball that prevents the ball from accumulating very much net charge. It tries, but the charge keeps going back and forth between me and the ball to the point where it erases any accumulation and nothing much happens. So what I have to do now is convey to you the physics of, okay, so why did that happen? You okay why the lightning bolts happened? It's a breakdown effect, and it happens when there's a certain strength of the pushes involved for the charges, which also stuff I have to talk about. But anyway, the point of this then is that it is possible to kill the accumulation. And that's actually something I've been dealing with up here. The fact that that guy doesn't send big lightning bolts at me suggests that it probably has some sharp things on it, or maybe I do, that I'm not holding a needle, but I've got something on me that's acting as a needle, or the ball's acting as a needle. This is why, to get this to work nicely, you have to have everybody nice and clean. No sharp stuff, no dust that has a little sharp point. All those sharp points ruin it. Okay. So to continue along then, so why does that point ruin the discharge, and how does that relate to xerographic copiers? Because so far I haven't said anything much about copiers. So we'll lead into that. And some observations about copiers is copiers consume a colored powder, typically black, but often can be other colors. It's called toner. So when your printer or a copier runs out of toner, what it's running out of is a fine powder that it's typically a plastic powder with color of some sort, black or the other colors. For an ordinary black and white printer, it's just black powder. After jams, so if you've had printers or copiers jam up, the paper didn't work right or whatever, and you pull out the copies or pull out the prints and stuff like that, there are times in which you can wipe off there's an image on it. You see, like, oh, okay, it almost made the copy. It almost did the job. And you rub your hand across it, it comes off on your finger. I hope that's familiar to many of you. That there's a transition period. There's a period during which the image is there, but it's not fused into the paper. It's loose on the paper. And what in the world would hold it on the paper? Could be static electricity. Yeah, it is. The copies are often warm after being made. That's less noticeable than it used to be, but it used to be they come out like hot to the touch, like, wow, burn your fingers. Same thing with the copies are sometimes clingy with static electricity. That too is much less noticeable than it was 30 years ago. They just keep on improving the techniques and getting rid of the things, basically burying all the physics and science so that it's more and more just magic. Copy comes out. The processes are still there, they just make them harder to notice. So the questions, not very many this time, is really how can light arrange color powder on a paper? And then we'll see that this leads to the question of how do you spray electric charge onto a surface, paper or otherwise? And just as a last sort of summary story is like, okay, so if you can get charge on a surface and you can arrange colored powder on paper, how do you get how do you finish the copy so that it's permanent, nothing wipes off? All right. So the story of how a xerographic copier works has a couple of pieces to it. And over the years, I've emphasized different parts of it and de-emphasized others or delayed them. I'll tell you the one I'm delaying right now shortly. But here's the basic idea of how a xerographic copier works. It has a very thin surface inside it somewhere. Sometimes that surface, the surface that I'm talking about or about to talk about, sometimes it's like a sheet or part of a belt. And other times, and most of the times now for most of the copiers you encounter, it's on the surface of a drum, a cylindrical drum. So inside the copier, you'll find a drum, clean, shiny, perfect little guy, and the surface that matters is a very thin layer of a plastic now. That's also changed over the years. It was various different chemicals or materials. It's now a plastic. It's typically green. It's got a green tint to it. You may have seen it in some of the changing the parts of a printer or copier. You'll see this cylinder, and it's got a metal surface underneath with a clear or transparent green, typically, layer on it. That layer's special. What's that layer? It's the layer that's sensitive to light, and it's called the photoconductor. So the material to follow this picture more than just the statement over here, the photoconductor is just terribly thin. I don't know whether it's thousandths of an inch thick. Should be flawless, thousands of an inch thick layer sitting on a surface that's metal. So here's the bottom layer. The bottom surface is metal, and beyond that, we don't care. The metal is the deepest layer that has any effect on the photocopying process. The rest is just support. So there's a metal layer coated with this photoconductor, and then it has a top surface is just there. You can touch it with your finger if you want to, but don't. That is the active surface. And what a photoconductor does is it makes a transition in the presence of light from being an insulator, that is something that does not allow charge to move and that therefore can hold static electricity, to a conductor. When you expose it to light, it becomes a conductor. Charge can move through it. And as a result, static electricity tends to move through it and get erased. So it goes away. So in the xerographic copier, the basic story of how the thing works is you start with this structure, the photoconductor sitting on metal, that by itself, that comes from the factory like that. And in the dark, you spray one type of charge. In this drawing, it's negative charges. You spray negative charges onto that exposed surface, the one you can see with your eyes if we turn the lights on. No light, though. It's in the dark. You spray negative charge on it, and because we're in the dark, the photoconductor behaves as an insulator. It's just like any old plastic, just sitting there. The charge accumulates on it. You've got static electricity there. All right? To make that charge more comfortable sitting there, because a whole lot of negative charges sitting on a surface can get pretty unhappy being near each other. They will tend to spread out funny, and the charge that accumulates on the surface won't be uniform because the guys at the edge have have fewer repulsive charges nearby. And this guy out here sees all those guys to her left, whereas this one in the middle sees all the guys left and right. These guys are much more unhappy than that guy. So how do you make this easier for everybody? Put metal on the bottom. And connect the metal electrically to the whole earth. What now happens is that negative charge polarizes the metal. The metal started with no charge on it. Nobody ever deliberately put charge on it. They just brought negative charge nearby. And the usual thing happens. If you bring negative charge near a neutral object, the neutral object polarizes. It brings all its positive charges near the negative charge, because that's good, and sends its negative charges elsewhere. And because this is a metal, which allows charge to move through it, that polarization is dramatic. If it weren't metal, if it were just plastic, the charges would move a tiny bit, but they can't move any long distance because it's an insulator. Because it's a metal, they can move long distances. So the positive charge comes in through a wire from the Earth and sits here right across from the negative charge, making the negative charge relatively happy because it's got attractive forces right near it. And where did the negative charge go? The negative charge left this metal through the wire and went as far away as it could. In concept, it went to the other side of the Earth. So should I show you this kind of effect? I'm trying to think, can I pull this off? Yeah, I think I could do this. Here, I want to show you that effect of if you bring charge near a piece of metal that's connected to the Earth, you'll pull opposite charge up onto the metal and send the light charge far, far, far away. Here's how I can do it. So this is insulated. It's sitting on a plastic stalk. And this guy's very good at showing us whether charge is around. Remember that story? If I deliberately put charge on it, bing, that little needle goes flying over. Okay? Let me get the charge off. I'm holding too much charge. I want to touch something that's connected to the Earth. This will do it. Okay. So I've got a wire that is in principle electrically connected to the Earth. Incidentally, we will talk about electric power distribution, and you've all seen electric outlets that have two vertical slots and a central pin, the three-prong plug stuff. That cylindrical pin, when you plug it in, that hole should connect by way of a wire to the Earth. It literally goes into the Earth by way of they'll drive a spike into the Earth, 10 feet of copper or something like that. There's some code for how you have to do it. But it connects to the Earth, which is not a good conductor of electricity, but it's decent. And so the result is that central pin is really connects you to the whole Earth. And this wire is trying to connect to the whole Earth, therefore. So what I was trying to do is let this charge leave by way of me. I'm not a very good conductor of electricity, but I'm not terrible. Are you going? Okay. So mostly it's gone. What I wanted to show you is this. Let me first start. Show you that assuming that I'll do the same thing. I'll let any charge that's on this go away. So this guy should have no charge on it. If you remember, if I went looking inside that cup, there's never going to be charge in there because the charge can always do better by going on the outside. So the charge is going to be the outside of any closed metal container. So is there any charge on this right now? No. Okay? So that's the point. No charge on this guy. I'm going to put charge on it without touching it with any charge. This guy's covered with negative right now, and I'm not going to touch the can. What I'm going to do is I'm going to touch it with my finger, and then I'm going to polarize it with the negatively charged stick. So I'm going to pull positive charge onto the can and push negative charge onto me, and then I'm going to stop touching. When I did that, I pulled positive charge onto that guy, negative charge onto me, and then I broke the connection. The negative charge is trapped on me, and the positive charge is trapped on it. It should have positive charge on it right now. Let me go see where I can find it. Oh, prove me wrong. Let's try a little more aggressively here. Yes, physics is saved. It's there. So I just want to make sure you can follow what I did. I took the can, which is sitting there isolated, no charge on it. I brought a negatively charged thing near it, and then I touched the can. And then I stopped touching the can. When I touched the can, the negatively charged thing attracted positive charge onto the can, out of me and out of the earth. So the can has positive charge on it because of polarization effects. We pulled positive charge onto the can and negative charge away from the can, and the can and the rest, can and me, we thought this was all fine and nobody was worried about it, and then we thought that charge stick would go away and we'd go back to normal. But before the charge stick went away, we broke the connection. And we made it impossible for the positive charge on the can to get back to the negative charge that had gone away from the can. We trapped it on the can. That's a trick known as charging by induction. I don't know, the name doesn't mean very much. I mean, you can write it down and go, oh, wow, now I know something. But the physics is much more important, that you can move charge around these sort of strategic ways. And they do show up in everyday life. As a brief aside to think of everyday life, years ago I got a call from what turned out to be a coal company, or I should say a mining company, that was having trouble with all their electronics getting just blown to smithereens every once in a while. Just like the parts would literally explode, and they couldn't figure out where this lightning bolt was coming from. And started talking to them about what they're doing, and they had rubber belts carrying mining stuff up from way down below and accumulating it somewhere up in the building. Rubber belts moving, and they were having various materials being carried and touching and going up into the building, and then there'd be a lightning bolt, bam, and blow out all their electronics. They accidentally created static generators like this. So once, having told them that, of course, it's one of those things like I told them what they had done, and they went, oh, we'll go see what that's the case. I never heard from them again. I'm pretty confident that was the case. They'd unplugged everything. There was nothing left except those belts were running. It had to be static electric. So knowing some of these things, the real world, they do pay off. Another example where that happens is printing presses. All the big belts of paper running around. This week, today's fake news. Today's, papers printing. You got to be very careful with those as well. The paper touching the metal rollers, the plastic rollers, you can move a lot of charge very fast. And before people figured out, they had to electrically connect all the printing press rolls so that one didn't go accumulate a lot of positive charge, the other negative. People would get killed by this. You get just tremendous lightning bolts would go across. Yet another case, cars driving down the road. The earliest of the tires were not electrically conducting at all. They were just really, really rubber tires. And you've got an insulated thing with a rubber tire moving around, and toll collectors would get blasted by someone come in to pay the toll on a car that was at minus 400,000 volts. Reach out, lightning bolts to the toll collector. So this too was solved by putting a little bit of connectivity in the tires. So the real world matters. Okay. So back to business here. Obviously I can get distracted on everything and tell you all these random stories. The issue with the xerographic copier is it takes that layer, that special layer known as a photoconductor, it decorates it with one kind of charge. In my drawing, negative charge. Positive charge is drawn into the metal layer by the process, basically this induction effect. Polarization and subsequently induction. So you have opposite charges sitting across on opposite sides, this terribly thin but insulating layer into the dark. Then you expose the layer to a pattern of light, and the pattern of light is either chosen by a document that you've put in the copier, and with the help of lenses, which we'll talk about late in the semester, with the help of lenses, you project patterns of light onto the surface. And wherever the light hits, which corresponds to a white spot on the document, the charge is able to move. So if you have light hit only over here on the left side of my little drawing here, the charges get together, positive and negative. They love each other. They go together and the static charge is erased. But where there was a letter, a black letter, for example, on the document, the light doesn't hit that portion of the photoconductor. It stays electrically insulating. No charge moves. And the result is that there's still negative charge sitting on that surface. And if you bring up positively charged plastic particles, the toner, they stick. They love to sit on that negative charge. They don't exchange the charge. They just sit there and sit next to each other and feel very happy until you then transfer that black powder onto a sheet of paper and then squish it or heat it, cook it into the paper so it's there forever. But that's the basic idea of a xerographic copier. Put a layer of charge on this open surface of plastic while it's insulating, and then use light to erase the parts of that charge where you don't want them. Yeah? How does light erase the charge? It turns out there are materials, I've described so far that the world sort of divides into materials that are electrically insulating and electrically conducting. It's more complicated than that. And we'll see that there's a whole world of what are known as semiconductors. Surely you've heard of semiconductors that have very interesting electrical behaviors just in general. Their structure's complicated. And we will look at them in maybe more detail than you ever thought you would want to know, because they're the basis for electronics. So if you want to know how your cell phone or computer work or your audio system, they're all built out of semiconductor devices. Transistors is sort of the classic component that does most of the work. So if you want to know how a transistor works, you have to look more in the detail at particularly this world of semiconductors. And a type of semiconductor, or semiconductors often have the property that they're in the dark, they are insulating, and if you expose them to light, there's some issues with what light you're using. They become electrical conductors. For example, what I have here is a cadmium sulfide cell, CDS cell. It's one of the earliest of the light sensors. So nowadays there's so much higher tech sensors, whatever. This is the classic simple thing to see whether somebody walked through a light beam, for example. And it is a semiconductor. It is a photoconductor. It's a material that in the dark it conducts almost no electricity, and when exposed to light it conducts electricity. And the right camera is this one. So now you're looking up. This meter here is showing you approximately how much light is hitting this little device. And if I block it with my thumb, we're down at 19 units, 1.8, that. If I let it see the room light, it sees more. And if I shine a flashlight into it, we're way up there. So what you're seeing with this is how well it conducts electricity. Let's let the charge move through it, and it's pretty much proportional to how much light it's seeing. Double the light, you get double the. It's twice as good at carrying electric charge. Is that okay? It's a simple preliminary description, but we'll come back to it when we start looking at semiconductors. You'll start to see the physics of why that happens. It's light energy freeing up electrons to move is what it's doing. The electrons, by and large, are sitting there in a situation where they can't move, which is typical of an insulator. But if you put in light energy, you shift them into a different situation where they can. And the more electrons you shift into that situation, the more electricity can flow through it. Other questions? Okay, so the two central issues in a xerographic copier, apart from just the mechanics and transferring plastic from here to there and all that, the two key things are the photoconductor, which we'll do properly later. I used to do it, now it's too early. And the other one, which might not seem like a problem at all, but it is how in the world do you put those charges on that open surface? You know, we just sort of took for granted that, okay, you put negative charges here on that open surface of the photoconductor. Well, what, you put them on with tweezers? You know, how do you get them there? It's an open surface. You have no direct access except the air nearby. And it is the air nearby. And the way they put the charge on, in a nutshell, is they get the air molecules to ferry charges onto that surface. So they have a source for the charges, in this case, negative charges. They put the negative charges on air molecules, and they have the air molecules go and land and deposit the charge on that open surface. So how do you get the air molecules to do that shuttling trick? And associated with that is some substantial physics. It's not a trivial thing to do. So, bottom line, the simple statement of the answer is they use what's called a corona discharge to charge the air. And a corona discharge is a way for charge to move from one surface to another without the lightning bolts. It's actually it's a stunningly self-limiting. It's not a spark. It's not like one of these snap lightning bolts, because that's a catastrophe where the more charge that begins to move, the more charge that begins to move, the more charge that begins to move. It's a runaway phenomena. The corona discharge is a very peaceful, self-limiting effect, and it happens in a way that's not a trivial way. What they do is if you take a sharp point or a thin wire, something that's very limited in one of the dimensions, and you pack a whole lot of charge on it by bringing it to either high positive voltage or a high negative voltage. If you bring it to a high positive voltage, it will eventually spray positive charges. If you bring it to a large negative voltage, it will spray negative charges. But it's a thin little thing, and when you do that on a sharp or thin object, the charge tends to leave the object for the air molecules because there's a ferocious push on the charge right there near the surface. And the origin of that push, the leaving process is called the corona discharge, but the origin of that push is the presence of a strong electric field. So electric fields, I don't know whether the term ever has floated past you before or not, but electric field is a complicated thing. It's not super complicated, but it's not trivial either. To understand electric field, which is the point of this whole story here, is that there are sort of two ways to look at the forces between these two charges. And I can't show you an electric field literally, so if you look at the figures online, the video figures where I've done animations, I can illustrate electric fields in animation that I can't show you in life because they're invisible. But here's the idea. That if I have two positive charges, as I've got here, of course they're like charges, so they repel. If I have to shove them together, don't do that, okay? So we can think of this charge on the left pushing directly on the charge on the right and vice versa. And that's all simple. It follows Coulomb's law. The forces get stronger as they get closer and all that stuff. But there's a second way to think about the forces between these two charges. And it seems initially like a stupid fiction, like why would we do this? And here it is. It's that this charge on the left creates a structure around it in space. That structure is known as an electric field. It surrounds the first charge. I'll put the second one down because I'm out of hands. So it surrounds this charge. It's everywhere in space. And at each point in space, it tells you how hard it will push on another positive charge and in which direction. So if I were to put a positive charge, and let this be a little what's called a test charge. A little charge, test charges are charges that are conceptual. They're dinky-dinky to begin with. They're always positively charged, and they don't create their own electric field. They're just observers. So if I have this positive charge creating electric field around itself, if I put this guy here, it's repelled, of course, because it is a positive charge. It wants to go that way. Wow. And so sitting right at this location is an electric field that has an amount and a direction. It's a vector. It points that way, and it's medium strong. It's not as strong as the one here. Ooh, this is tremendous because it's too close to the other positive charge. So this is a big, strong vector pointing in that direction. And down here, there's the vector points down that way, and it's not, it's medium close, so it's got sort of medium strength. And out here, it's weaker. You can't even see it. So at each point in space, there's a little vector pointing, showing you how hard it pushes on a charge and in which direction. So it's what's called a vector field. It's everywhere. It's also in 3 dimensions. It's a big, messy thing. Okay? And the result is that this charge on the left creates an electric field around it, which in turn pushes on this charge on the right. And that means that the forces between these two now has this intermediary. This one creates the electric field, which pushes on that one. And of course, this guy also, not being a test charge, being a real charge, it creates an electric field too, which pushes on this one. It's all nice, and they both work. But the electric field seems like I'm terribly, why did you put that in there? It just makes life more complicated. Can you visualize the field a little bit? Or questions about the field? It's hard to, what kind of question can I ask to evoke any response? Who knows? Why would you create this thing, this electric field, around this guy and around this guy? It's so complicated. Because of at least 2 reasons. One is, there are other ways to make that electric field than having a charge. You can make an electric field that it pushes on this guy without any charges. You can do it using magnetism, as we'll see down the pipe. Okay? So the first thing is that the electric charges aren't the only source of electric fields. The other thing is, a seemingly strange observation. What if I have these guys pushing on each other, and this guy on the right knows the one on the left is pushing on it, and I whisk the left part charge away. I pull it away really fast as nature will allow me. It's going to, so I've done that. The charge on the right will not know that the charge on the left is missing for a brief period of time. It's not instantaneous. They are not reaching across space and pushing on each other. They are creating an influence that ripples out and takes time to go from one to the other. How much time? Well, these guys are maybe 1.5 feet apart. And light, remember light? Which doesn't seem to be part of the story, but it is. Light takes about 1.5 nanoseconds to go from this charge to that charge. Is speed of light, remember speed of light? That means that when I whisk this guy away, it takes about 1.5 nanoseconds for the charge on the right to notice something happened. Because the influence actually travels at the speed of light. It's a special speed. It's not just about light, it's about a lot of stuff. And the fact that this guy being whisked away leaves this guy still thinking, hey, everything's good. It's not long, but it's just thinking, nothing changed. Hey, we're business as usual. Means it's being pushed on not by that charge, but by the electric field this charge created around it. And it takes a little while for that electric field to change. Is that okay? I mean, it's weird, but it is what it is. All right, we'll continue along this vein on Wednesday.